All right, so I guess let's go ahead and jump in. For those of you who don't know me, I'm Eric. I work at UCLA on the pyspedas team. And today we're going to cover a tutorial of pyspedas. And really, it's also a tutorial of pytplot. So I have examples of loading the data with pyspedas and working with that data using pytplot. And I have my email up here. I uploaded this whole entire presentation to the presentations folder on the website. So all these slides should be available to review afterwards, or currently if you want. So just an introduction to pyspedas. We currently support Python 3.6 and later. We recently dropped support for 3.5 because some of the libraries we depend on drop support for 3.5. We have a MIT license, so permissive license, and we're cross-platform. It works on Windows, Linux, and Mac. Most of our users are on Windows and Mac, although I also get support requests from Linux from time to time. So it definitely supports all three of those. And we're distributing it on GitHub or we're doing all development on GitHub, and that's what we're treating as the bleeding edge. And we're also doing releases on PyPI. And we currently support loading data from 23 projects covering more than 130 different instruments. So I think there's actually more data you can load in Python now than our IDL tools. So installing, just getting started, if you haven't installed it before, you can just do pip install pyspedas. If you do have it installed, you might want to use upgrade to get the latest version. So it's just pip install pyspedas -- upgrade. And internally, pyspedas uses pytplot to load the data into variables and create plots and actually work with the variables. And they're doing development on GitHub as well. It's just github.com/mavensdc pytplot. And they also have documentation at Read the Docs. And we don't have a Read the Docs yet for pyspedas, but soon. And pytplot supports CDF files, netCDFs, IDL save files, and STS files. And internal to pyspedas, we also use pandas to load some limited ASCII data sets. For example, the MMS ASCII state files released by their flight dynamics team. And for those of you unaware, pytplot's based on IDL-tplot, which was originally created by Davin Larson in 1995. And so it has around 25 years of usage in space physics. And the T in tplot stands for time. So all these variables we're talking about are time series data. And pytplot variables combine the time series data and the metadata on, so for example, like the plot metadata of the coordinate system. So here's a full list of the missions supported. I'm going to go through in the following slides with more details on the instruments. But the thing to note is that while we support loading the CDFs for most instruments on these missions, the post-processing of the data products for most missions aren't the same fidelity as our IDL tools yet. The one big exception is MMS, because I've been working with the MMS team to actually get the same fidelity of our IDL tools. So with the exception of analysis tools for distribution functions or plasma distribution functions from MMS, we pretty much support all the same data products and tools for that mission. And the other ones are coming along. So I have a full list of the supported projects and instruments. So we support ACE data, Arase data, cluster data. And the Arase data comes from their data center in Japan. The cluster data actually comes from SPDF at the moment, but I'm hoping to add the European data set or the European data center as well, because that actually has more data sets. We support SWE, which is a CubeSat from Colorado. We support Discover data, Equator S, FAST data, GeoTail. We have the GOES magnetometer data. I still need to add the X-ray and the particle data for GOES. And the GOES data loads from NOAA. We have the energetic neutral atom data from IMAGE, as well as the EUV, FUV, RPI, as well as their orbit data. We have a bunch of different instruments from Maven. We have MICA data. That's the magnetic induction coil array. It's a data set released by the University of New Hampshire. And I mentioned we have support for all the MMS instruments. This also includes team-only data, so quick look data, the scientist in the loop data, the latest L3 data products, and as well as the state data. I mentioned the ASCII files. We have Omni data, so it's just the Omni solar wind data that's time shifted to the magnetopoles. We have the POSE space environment monitor. We have Polar and all their instruments, as well as their ephemeris data. We have the Parker Solar Probe data. We have RBSP, it's the Van Allen probes. Stereo, the stereo mag data, I think, loads from Berkeley, and the stereo plastic data loads from NASA. We have the Themis data, which also loads from Berkeley. That includes our ground magnetometers, the moments data, the ground computed moments. And right now we're limited in our post-processing for Themis data, so it's you really want to access the L2 data. We don't have post-processing for, say, calibrating the L1 data yet. And we have the TWINS energetic neutral atom imagers and the Lyman alpha detector. We also have Ulysses data, so that older data set, and we have WIN data. So by default, the data are placed in the directory where pyspedas is installed, and you can configure this with the speedas data dir environment variable. Most missions also have their own environment variables which override speedas data dir. So you can set MMS data dir or them data dir to put the MMS data directory someplace else. An important thing to note is that all these environment variables also work in our latest IDL versions. So if you load data in IDL, pyspedas should automatically find those data files locally, and the opposite is true. If you load it in pyspedas, IDL should automatically be able to find it as well if you set those environment variables. And the data sources depend on the mission. For MMS, the default data source is the official Science Data Center at LASP. But you can also load the data from NASA SPDF using the SPDF option to the load routines. I think the Arase data comes from Japan. The GOES data comes from NOAA. Most other missions, but not all, load the data from NASA SPDF by default at the moment. And the data are loaded by functions that follow the general form pyspedas.mission.instrument. So for example, for MMS FPI data, it's pyspedas.mms.fpi, or RBSP emphasis data, it's just pyspedas.rbsp.emphasis. And one thing to note is that you can also, instead of just importing the top level pyspedas and having to type that every time, you could also say import MMS from pyspedas and then just call mms.fpi to load the FPI data. You can also load or do the import as import FPI from pyspedas.mms and just load that function. So it's pretty flexible in how you actually import the load routines. And the load routines support local caching, which matches the remote directory structure. And those also match what we do in IDL. And we always download the files to temporary files to avoid partial downloads. So this is to avoid, so if you're say downloading in an airport and a file download fails, you don't end up having a partial CDF file in one of your directories, which can cause you to crash the load routines. We also support loading the files without an internet connection, and we support downloading the files without actually loading them. Support usernames and passwords, just using standard HTTP authentication. And we also support loading the files into NumPy arrays without creating tplot variables. And I mentioned earlier that we have this username and password. And for instance, if you try to load MMS team-only data, like quick look data or scientist in the loop data, you'll have to it'll prompt you for a username and password before you can actually load that data. So just like with our IDL load routines, the options are set with some standard keywords. So for example, tRange, that's the time range. The thing to note about the time range is that it's the first element is inclusive and the second element is exclusive. So in this example, you would load data from December 15th for the day of December 15th, but you wouldn't get any data for December 16th. And we also have a keyword time clip, which clips the data to the requested time range. By default, most load routines will go out and find all the data files that have data within your requested time range and dump the entire data files in. And we don't time clip to the requested time range by default because it can take a lot of time to actually do that time clipping. Some load routines do set the time clip by default though. And that's really controlled by the instrument teams. If they, some of them prefer to time clip the default or time clip by default. Most load routines also have a level, so supporting the level of the data, for example, L2, L3, quick look. And all the load routines also have a no tplot keyword, which loads the data into NumPy arrays and hash tables. And I'll show an example of that. We also have download only. That means tells the load routines to download the files, but don't load them. So in that case, the load routine doesn't actually load the tplot variables. It just goes out, grabs the files and saves them locally, and then returns a list of the files that it loaded. We also have a var format, which limits the variables loaded using Unix style wildcards. So if a CDF file has like 1,000 variables in it and you only really want one variable, you can set the var format keyword to only load that one variable, and it'll save a lot of time on actually loading the data files. We have the no update keyword, and this tells it to only load the data if it exists in the local cache, so it doesn't actually go out to the web and try to download the files. And there's a suffix keyword, which appends a suffix to the variable names. And there's a lot more keywords depending on the mission and the instrument. So to see the full list of keywords supported by a load routine, use the Python help function. So for example, it's just help pyspedas.mms.fbi once you have pyspedas imported. And here's an example of what happens when you call help on pyspedas.mms.fbi. So you can see that for all the MMS load routines, we also have probe for setting the probe number, data type, data rate, and there's also an available keyword to list the available data files without actually downloading them. And this is only a partial list. If you were to, there's actually a lot more for MMS that allow you to control, say the CDF version, the exact CDF version. And one thing to note is that by default, when you call one of these load routines, they actually have defaults for all of these. And so they load some default data. So you don't actually have to set any options. If you just call pyspedas.mms.fpi, it'll actually go out and load some default data. So here's an example of MMS FGM data. So all I did was import pyspedas and then call pyspedas.mms.fgm. And in this case, we're set the data rate keyword to burst and the time range to 1 minute. So we're loading 1 minute of burst mode data for FGM. And it went out and downloaded the data file, then loaded them into pytplot variables. And it also returned the list of pytplot variables created. And to plot the data, we just import tplot from pytplot. So we say from pytplot, import tplot, and call it on the variable names that you want to plot. So in this example, we're plotting the B field and GSE coordinates on top and the B field and GSM coordinates on bottom. And note that I didn't actually set the probe number here. As I mentioned, there are defaults. The default here for probe is just 1. Here's the result of that tplot call. It plotted the GSE coordinates on top and the B field and GSM coordinates on bottom. And the metadata was automatically set. And note that, remember I mentioned the time clip keyword. Since we're not setting the time clip keyword, we actually got longer than 1 minute of data, since there was more than 1 minute of data in the CDF files covering that minute. So we actually ended up with 2 minutes of data. But if you set the time clip keyword, it would actually clip it down to 1306 to 1307. So here's another example with MMS FGM, and this time we're actually setting the probe keyword to all 4 probes, so 1, 2, 3, and 4, but requesting the same time range and setting the data rate to burst. And it goes out, and since I already had the data file stored locally, it's just loading the data files. And it loaded the data for all 4 spacecraft. And in this example, I called tplot on the B field and GSE coordinates for each spacecraft. So it's MMS1 on top, followed by MMS2, followed by MMS3, followed by MMS4. So to access the data values from a pytplot variable, you just use get underscore data from pytplot. So in this example, we import get underscore data. We just say from pytplot import get underscore data. And that by default, that returns a tuple containing each of the data. The first element is always going to be times, and then for a line plot, the second element of the tuple is the actual data. And the times are stored as Unix times. And if this were a spectra variable, it would be 3-element tuple. So the first element will be time, second element would be the data values, and the third, if it were energy spectra, the third element would be the actual energy values. And so we need tools to actually work with those Unix times. So we have a function called time underscore string, which converts the Unix time to a string. And we have time underscore double, which converts the string back to a Unix time. A user also contributed time underscore date time, which converts it to date time objects. So here's an example. You just from pyspedas import time underscore string and time double. And I gave it the times variable the first 5 times from that previous example, and you can see it converted it to strings. And then I converted it back just using time underscore double. And the opposite of get underscore data is store underscore data. So you just import store underscore data from pytplot, and then the first argument is just the variable name that you want to create, and the second, then you set the data option to a dictionary containing the values you want to store in the variable. So the X key maps to the times, and the Y key maps to the data values. So I took the data from that we used in get data returned it before, and created a new variable called FGM B field GSM. And it created the variable, and then we called tplot on that new variable, and it created the plot. And the important thing to note here is that the metadata wasn't set automatically, since we didn't update the metadata. And I'll show how to update metadata on pytplot variables in an example soon. But to list the variables currently loaded, you use tplot underscore names. So you just import from pytplot, import tplot underscore names, and call tplot names. And it actually shows a list of all the variables loaded, as well as numbers, indexes for each variable. And the variables can also be referenced by that number in calls to tplot. So you don't actually have to type out the full variable name. You could just say plot tplot 10 will plot the, in this example, it'll plot the ERG and GSE coordinates. So here's an example of loading electric field data from MMS. So we just call pyspedas.mms.adp, because EDP is the name of the instrument containing the electric field data. In this example, we just set probe equals to 4 to load MMS4 instead of the default of 1. And again, this is burst mode data for that same time range. And in this example, so for EDP, I actually automatically time clips the data, and that was requested by the team. So then we call, again, just call tplot on that variable, on the electric field variable in GSE coordinates, and it creates a plot showing the electric field in GSE coordinates. And you can see some spikes close to 1307. So if you want to clip a variable, you want to remove some of those spikes, there's a tool in pytplot called clip. So you just import clip from pytplot and then call clip on the variable you want to clip. Give it, the first argument is the name of the variable, the second is the minimum, and the third is the maximum. So in this example, we're clipping the GSC electric field data down to -50 to 50 and removing all data points outside of that range. And then you just call tplot again on that variable, and notice that the values outside of -50 to 50 have been removed. So here's an example of FEEPS data. It's the electron energetic particle detector on MMS. Again, it's just pyspedas.mms.feeps. And again, we just set the probe to probe 4, and we're loading around 1 minute of burst mode data. And important thing to note is that this simply isn't just loading the CDF file into memory. There's a large amount of post-processing done here, including energy table corrections, flat field corrections, known bad channels are being removed. The integral channel, there's an integral channel on all of these variables tacked onto the end. That's being removed and split out into its own variable. The sunlight contamination is being removed based on a model developed by the team. We're calculating the omnidirectional spectrograms and spin averaging those spectrograms. We're also setting the metadata automatically on loading. So there's a lot happening behind the scenes other than just grabbing the CDF files and loading them into memory. And all of that results in, you can just call tplot on the omnidirectional spectrogram, and it'll create the plot. And it's the same plot as if you were to load from IDL, from our IDL tools. And I didn't plot the spin average here since this is burst mode data. Spin average data doesn't really look all that good because it's such a small time range, and the spin's 20 seconds. So here's an example from MMS FPI, so the fast plasma investigation. Again, it's just pyspedas.mms.fpi. And in this example, we're loading 2 different data types, the electron moments and the ion moments. And we're doing probe 4 and burst mode data for that same time range. One important thing to note about the plasma data on MMS is that the plasma measurements are actually at the beginning of the accumulation interval. So if you load FPI or HBCA data, you have to set the center measurement keyword to true to actually center those measurements to the middle of the accumulation interval. So if you were to say, want to calculate plasma beta using FPI and FGM data, you would have to actually center those measurements because the FGM data are at the center of the accumulation interval. And that just uses the metadata and the CDF files to center those measurements. So just plotting that data from the last slide, we're plotting the electron number density on top, the electron bulk velocity in the middle, and then the electron omnidirectional energy spectra on the bottom. And if you were to create the same plot in IDL using our tools, the plot would look almost identical, if not identical. And here's an example of plotting the ion data that was also loaded in that same call. We have the ion number density at top, the ion bulk velocity in the middle, and the ion energy spectra on the bottom. So here's an example of loading Themis FGM data. So, and in this example, we're gonna not load it in the pytplot variables. We're gonna use no tplot to return the data in hash tables and containing the numpy arrays. And we're gonna use var format to only load a certain variable. So in this example, we say Themis D underscore FGM is equal to pyspedas.themis.fgm. And then we set the no tplot keyword and the var format keyword, and we're loading probe D, and the day is November 5th on 2013. And since I already had the data file locally, it went out and found the data file and discovered that I already have it locally and that it's current. So it says file is current, and then loads that file. And so when you call, and it's it actually when you set the no tplot keyword to true, it returns a hash table of hash tables. So the first hash table has the keys or the variable names mapped to another hash table with the x, y, and v. I think v in this case is just 1, 2, and 3. For some reason, there's a depend 1 on these files. But the x are the times, the y are the actual FGS values. So you can access the NumPy arrays just by referencing those hash tables. And again, this doesn't load the files into pytplot variables at all, so you can completely avoid pytplot variables here. And if you didn't set the var format keyword here to load that one variable, it would load all the variables in the files. But at the top level, it's really it only has that one variable because we set the var format keyword. So here's an example of loading Omni data, SolarWind data. So it's pyspedas.omni.data. You just set the time range. And in this case, since the files are monthly, it actually does time clip by default. That way you don't get a full month of data every time for every day. So if you request a day, it actually time clips down to 1 day. And here's an example of plotting that SolarWind data. So you just call tplot on the variables, and we have SimH on top, and then SolarWind proton density, followed by the SolarWind flow speed, and we're plotting BZ and GSM coordinates at the bottom. And again, that's just a day's worth of data. Here's an example of loading geotail magnetic field data. It's just pyspedas.geotail.mgf. And in this example, we're loading 1 hour worth of data and setting time clip to true so that we time clip down to that 1 hour. And it found the data file locally, so it didn't actually download the data file. It just set the if modified sense when it was trying to download it, and found that it was already, that the file in the cache was already current. And then it loaded them into pytplot variables and did the time clip, and it loaded all of the variables. So then we can call tplot on those variables. The first is the magnitude, the second is the B field vector, and the third is the position vector. And by default, the colors for a vector are black, red, and green for X, Y, and Z. So black is X, red is Y, and green is Z. But we tend to change those and set those after loading the data. For instance, for MMS, we use blue, green, and red. And we're going to slowly move that to blue, green, and red to match the way things look in IDL. But you can set plot options using the options function in pytplot. So for example, you just say from pytplot import options, and then give it the variable name as the first argument of the option that you want to set, and then the values for that option. So for instance, in this case, we're setting the vector, the B field vector colors to blue, green, and red, and the position vector to blue, green, and red. And then we call pytplot on that same plot as before. Notice that the colors have been updated to blue, green, and red. And there are many other options. You just use help on the options function to find the full list. Of course, it's just stored in the doc string. So you can change the color map, which is the color table. You can set a log scale on the y-axis, a log scale on the z-axis, and turn those off. You can change the character size, the line style, the name, the z range, the y range, z title, y title, the Y subtitle, C subtitle. So here's an example where we change the Y title on those previous plots. So we set, instead of using the variable name, we set the Y title to geotail bmag and give it the units. And we update the B field vector Y title to geotail bvec with the units, and then the position vector with just geotail position. And we also set the legend names, which is the labels on the right hand side of the figure. So we update the labels to bx, by, and bz for the B field, and the position x, y, and z for the position. And then we just call tplot on those variables again. And now we've updated the plot with that metadata. And you can also set global plot options. So for instance, the title of the plot with tplot underscore options. So you just import tplot underscore options from pytplot and then make a call to that function with the option you want to set. So for instance, title sets the title, and then call tplot on the variables you want to plot. And the title now has, in this example, we use geotailed data. And there are many other options. So for instance, you could change the size of the title to 20. We're changing it to 20 characters. So it's tplot options title size 20. And you can set a region of interest for the entire plot by just setting the ROI option and giving it the time range. And then again, we just call tplot on the variables you want to plot, and it includes the updated title size and the region of interest. So here's an example of loading Arase data. So we just call pyspedas.erg.mgf and set the time range. And by default, it'll load a default time range. But I've been setting time range as an example, or in all of these examples. But you could just call pyspedas.erg.mgf and it'll just load some default data. And I mentioned earlier that the Arase data is loaded from Japan. So you can see it's actually going out to their data servers in Japan and finding the data and then loading them into tplot variables. And again, we just call tplot on some of those variables loaded, and it creates the figure. So in this example, we're plotting the B field in GSE coordinates and GSM coordinates and in SM coordinates. And to load RBSP emphasis data, that's the B field data from RBSP. We just call pyspedas.rbsp.emphasis, set the time range. In this example, we're setting the data type and the level to L3. There are a bunch of different levels and data types, and emphasis also supports a coordinate keyword to change the coordinate system. And the default is just SM coordinates. And also supports a probe keyword for changing the probe, and by default just loads probe A. So in this case, it loaded probe A, the L3 emphasis magnetometer data, and SM coordinates. It created a mag variable, a magnitude variable. That's the B field magnitude and the B field magnetic vector. And then we call tplot on magnitude and mag, and you can see it creates a plot with the B field magnitude on top and the B field magnetic vector on the bottom. So if you want to load discover data, it's just pyspedas.discover.mag. And notice that the names of these instruments all follow the instrument names provided by the teams. So for MMS magnetic field data, it's FGM. For Arase data and geotail data, it's MGF, and Discover data, it's MAG. Those just follow the naming convention of the team, or set by the team. So in this example, we load 1 day's worth of data, November 5th, 2018, and I already had the data file locally, so it just found that the data was already there and used it. And then we plot the B field data by just calling tplot on that on the B1 GSE variable. To load the Faraday cup data for Discover, it's just pyspedas.discover.fc. Again, just following the naming convention of the team. I think in IDL, we do something very similar with the naming conventions. Loading the Discover data, it's pyspedas.discover.fc, and set the time range, the same time range as before, and already found the Faraday cup data locally, and just loaded the variables. Then we have the VGSC, the thermal speed, the number density, and thermal temperature. And then I called tplot to actually create on those, to actually create that plot. So one useful common routine or common tool is to take vectors and split them into components. So rather than having to use get data and store data to actually work with vectors, pytplot has a tool called splitvec. So you just import splitvec from pytplot and call it on the vector you want to split, and it creates components from the individual components of the vector. So it creates new tplot variables with the component data. It just depends X, Y, Z components to the name. So in this example, we took the VGSC loaded from the Faraday cup data from Discover, and we just fed that to splitvec, and it created 3 components. So the X component, the Y component, and the Z component. And then we call tplot on those components to actually create the plot. And the opposite of that is creating a vector from its components. pytplot has a tool called joinvec. So you just import joinvec from pytplot. And then you just call joinvec on the variables that you want to join together. And by default, it just appends the variables together and adds an underscore joined at the end. There's also a keyword that allows you to set the name automatically. In this example, I just let it use the default. And then I called tplot on the joined vector. And so now it has the updated, and it now has all the components as a vector again. And it should match the same as before. So here's an example of loading some stereo mag data. So in this example, we just call pyspedas.stereo.mag and set the probe to B. By default, I think it loads probe A. And in this example, we're setting a suffix on the variable names. So we're setting suffix equals underscore behind, and then giving it 6 days instead of our standard just 1 day. I think all the previous examples were showing just 1 day or 1 day, but you can load multiple days. So in this example, we're loading 6 days of data, and you can see that since the data files are actually daily, it looks like I already had 2 of the data files already stored locally, and they were current. So it just loaded those 2, and then it went out and downloaded the data files for the dates that I didn't actually have stored locally in my cache. And then it loaded the data into a tplot variable and appended the suffix underscore behind. And then I called tplot on this new variable, and it created the plot for the B field for the 6 days worth of data. So we also support the energetic neutral atom image data from twins. So it's just pyspedas.twins.imager, and set the time range. By default, it loads twins 1. You can also set the probe to 2 to load probe 2. And one useful thing here on, so get data actually can return the underscore or the underlying X-ray object. So internal to pytplot, all the data are stored as X-array objects, and you can actually access the X-array data array just by setting X-array to true. So in this example, we loaded twins DNA data for 1 day, and then we called get data on the smoothed image. This is the number of counts, and we set X-array equals true, and it returns the X-array object, which has the metadata and the data values. And of course, you could then work with the X-array object, doing things like time interpolation. So here's an example of loading Parker Solar Probe data. So in this example, we just call pyspedas.psp.fields to load the fields data. And instead of loading into pytflat variables, we're setting the download only keyword. So now we're not loading into tplot variables, we're just downloading the data files. And I think I did 2 days worth of data, the 5th and the 6th, November 2018. And so we actually already had I already had the data files for November 5th stored locally. So it just went out and found that those files are current. And then it downloaded the data files for the 6th. And if you set the download only keyword to true, it returns the list of the files instead of, so it just downloads the data files and it doesn't actually load them into anything. But so the return value is just a list of the files that were downloaded. And then on the bottom, we're loading the solar probe cup data. And again, we're setting the download equals true and just downloading the data file. So to find more examples, we're using Jupyter Notebooks to create examples. So to find these, just go to the SpeedS organization on GitHub. It's github.com/SpeedS. We have 2 main folders for these. One is pyspedas_examples. These are general examples for various missions. And we also have MMS-specific examples under MMS-examples. We have so many for MMS that really justifies having its own repository. Here's an example, one of the Jupyter Notebooks for MMS that applies the curlometer technique to FGM data. So you just load the data, the FGM data, and then you apply the curlometer technique using the curlometer function. So we're using GitHub Actions to run unit tests that load the data. We currently have more than 80% test coverage. So every time we commit, it goes out and runs the test suite and loads the data and checks if the data were actually loaded. And we're also validating the data products match those from IDL. And we're doing this from IDL. We use the MG unit test suite in IDL to run tests in IDL. So here are some examples from MMS. We actually have this function called SPD run pi validation, which takes 2 main arguments, 2 input arguments. The first is a list containing the input, or essentially the Python script, and then the second argument, it's a list of variables to check. So the first up front, what you do is load the data in Python, or load the data in IDL, and then you pass it a script. You pass SPD run pi validation a script that loads the same data products in Python, and you pass it a list of variables that you want to check to make sure that they actually match. And we have more than 20 of these in IDL so far, just for MMS. And MG unit makes it really easy to, when you're using MG unit, you can just call make a single call, and it runs all the validation tests in one run, and it outputs the status of the tests. So future plans, we're going to be adding a happy client soon to bring happy data into pytflat variables. This is really just a wrapper around the official Python happy client that'll actually just load the data into pytflat variables. And we're going to be adding more projects soon, like solar orbited data, barrel data, and we need to add a lot more post-processing, starting with the thinnest calibration, and we're going to add more post-processing for ERG. There's a lot of post-processing there in our IDL tools that's missing from Python, and we need to set a lot more metadata on load. So for instance, loading or setting the plot metadata like the Y titles and the colors and making sure everything's consistent. And I keep getting requests for adding 2D slices of distribution functions. So that's coming soon. Oop, I skipped that last one. So how to contribute, get in touch. If you have options, or if you have if you want to have something you want to contribute. And I just listed some potential ideas for contributions. For instance, post-processing to the current load routines, new analysis tools, or new example notebooks, or documentation updates. I'm sure there are some problems with some of our documentation. And as well as PyTplot and CDF contributions, since we rely heavily on PyTplot and CDF. Any contributions to those would be greatly appreciated. So that's all I have. Let's see what the chat says. All right, so are there any questions?
You know, I have one question I'm curious about. Obviously, this project grabs a bunch of different data sets from different data providers and kind of puts them into one central way to access them. Just from a high level, what did you find was the hardest part of trying to like unify disparate kinds of data sets? Because I know data providers often do lots of different things with their data.
I think the hardest part is probably actually being handled by CDF lib and actually handling all of the different types of data files. So the hardest part is really done by the CDF people and the PyTplot people. Downloading the data files is really simple, and accessing the data files also really simple. But that's mostly based on our experience with IDL. I mean, we do all the same stuff in IDL. And so we have a lot of experience behind the download routines, so we know exactly what to actually implement. So yeah, the hard part is really in the libraries that we depend on, and our work has been very easy thanks to PyTplot and CDF lib.
Oh, great. Well, that makes sense. Yeah. Thanks.
Yep. And there was a question in the chat: is the same data cleaning performed when download only equals true for loading data in the tplot? And so if you only download the data files, it doesn't actually do any post-processing to the data. So no, the answer to this is the same data cleaning performed for download only is true is no. It only downloads the CDF files and doesn't load them at all. However, if you set no tplot equal to true, it should do the same data cleaning, I believe. Although actually no, a lot of them might be wrong about that. So for instance, for MMS, you set no tplot equal to true. I don't think it does say, for instance, flat field corrections or any of the extra stuff. Because a lot of that depends on actually using tplot tools and tplot.
But maybe the question was about if you just download and then load it later, are you still gonna get the same clean? It eventually takes it through the same cleaning, I assume.
Yeah. If you download the data and then load it later, it will do the same thing, or the same post-processing. It's just the post-processing requires on it actually actually loading the data into PyTplot variables.
Right. So if you wanted to save your own cleaned data, you could output the tplot variables, but otherwise the files you're getting are just the raw files that came from wherever the data provider put online.
Correct. Yes.
Is there an output mechanism for the tplot variables?
That's a good question. I don't think, I think internally in pytplot, there might be a way of saving the variables to CDF files, but I haven't actually experimented with that too much or at all.
Mhm.
And so Rebecca asked another question: how would one get the clean data apart from tplot? Right now, you really have to use tplot to do that. I suppose you could, since we have a permissive license, you could actually just rip the code and implement it yourself outside of it. But I wouldn't suggest that because we frequently get updates from the team, and so those codes get updated. For instance, I wouldn't be surprised if there were updates to the sun contamination routine for FEEPs at some point in the future. So any other questions?
Did you answer the question in the chat? How would one get the clean data apart from tplot?
Yes.
Okay, cool. Just check.
So how many people are working on the pyspedas code base?
So there are two of us mainly, as well as currently actively working on it. We have contributions from all over the place. The Maven code was provided by the Maven people, Brian Harder and Julie, as well as I'm sure there are more people behind all of that. And we've received a lot of contributions, both through GitHub as well as from people on email, like the mission and instrument teams have been using it. So you can see we have, I think there's technically 7. One of these is duplicated, 7 contributors. But again, this isn't all inclusive. There are a bunch of other contributors who send emails, and we have a lot of scientists who don't actually use GitHub, and so they just email changes and suggestions.
Yeah, that's great.
And I didn't mention the documentation, but if you go to the current way we're doing documentation is on our GitHub. If you just go to github.com/pyspedas, and we have the, just click the pyspedas repository, and in that README, we have a list of the missions, and each one links to documentation for that mission. So you can just, for instance, go to the Discover mission, and it has the instruments supported as well as some examples. MMS, we have a lot more documentation since it's the furthest along. We have what's included. You can see we can calculate the HBC omnidirectional spectrograms, do FEEPs and EIS pitch angle distributions, create orbit plots, do kilometer calculations, limit the CDF file versions with using a variety of keywords. And then there are, of course, examples for each instrument. So that's pretty much all I have. If there aren't any other questions. Thanks for listening and for following along. And of course, you can always email me afterwards if you have questions. It's just egrimes@igpp.ucla.edu. And again, I uploaded this presentation to the presentations folder on the meeting website.